Okay, so the third speaker of session 1, part 1, day 5 of the Congress is Ken Millett from the University of California, Santa Barbara, who is going to talk on the home flipped polynomials and the Conway and Kinoshita-Terasaka knots. Ken, is to you.
Thank you very much, Sophia. Let me just play here with
Needless to say that Ken is the M in conflict.
Yeah. Okay. I think this should work well. Oh, there, move my screen a little bit. Yes, well, it's a great pleasure to join everyone in wishing a happy 80th birthday to Lou Kaufman. I'm one of those who've known Lou since the time he was a graduate student, I think, roughly back then. We won't figure out exactly when. I tried to find a picture of him, and the earliest I could do was the 90s, actually. And of course, you can see he hasn't changed all that much despite the years. He's simply gotten, like good wine, better and better as time goes on. So today, I just want to share with you some thoughts about applying these knot polynomials to the study of open knots. This was inspired by the work of Willie Taylor, who is the first person to have been convincingly able to show us that there were knots in proteins. And that was, for me, the catalyst that motivated me and in much of my work since then. And so I'm going to tell you a little bit about that odyssey and some applications that date from 2020, from the COVID years when I was isolated in Santa Barbara. And in a large sense, I'm going to report on sort of progress, but I've rather pretty much abandoned being retired now since 2017 or so. And so I will leave you with some questions and hopefully stimulate further thoughts that some of you may have about how to apply these polynomials and some of the ongoing mysteries. And so I'm going to try to, okay. And I can actually change the screen. So I'll start with a brief review, historical review, and then I'll talk about some of the efforts to understand the geometry of open knots. Much of this work is based on discussions with Eleni Panagiotou, which began before COVID, continued during COVID, and a little bit since then, since I've retired. So I've left a lot of this sort of in progress, as it were, with no intention of really devoting the necessary energy. So a brief overview, we'll talk about the knots, the sort of business about the polynomial, how we approach the analysis of open chains, leading to some concepts that we've called the knot spectra, the superposition of the spectra, and then the analysis of the data, and then very simple applications to the Conway and Kinoshita-Terasaka conformations. So let's see. Okay, yes. So from those of us from a certain era back, then the Conway knot and the Kinoshita-Terasaka knots were very, very interesting and very puzzling to us. And even at the outset, we it took a fair bit of effort and a rather important paper by Bob Riley in 1971 that proved that the knots were in fact different because he could calculate, showed us how to calculate and distinguish the knot groups, the fundamental groups of their complements. These knots are related by mutations, and that you can see in this picture. In the circle, we've taken that portion and done a sort of vertical 180-degree rotation. So that was the notion, goes back, I believe, perhaps to Conway, of mutation of these knots, and are different. Below them, I think I've faithfully copied the Humphrey, I can't pronounce the PT either, I'm sorry. But anyway, that polynomial, I think I've gotten all the coefficients there right. That's always to be seen. That we know early on in early days that if you have a mutation, the polynomials are absolutely identical. So you can't use polynomials to distinguish them. But fortunately, we've got from 1971, the fact that the knot groups were different. Okay, and I better watch the time a little bit. I'm not going to have that many slides, but I'm notorious about forgetting the time. So another, remarkable event, certainly Bob Riley's was something that happened during my mathematical lifetime, but also David Gabay, using foliations, was able to then, in his PhD thesis actually, show that they were different by actually calculating the genus of the two knots. And here are pictures showing the Kinoshita-Terasaka knot is a genus 2 knot with the genus 2 surface, rather complicated. And the Conway knot is genus 3. Looking at these, I should also say that the images that I'm sharing, I've gotten from all sorts of places, and I frankly don't recall exactly where, but this could have come from Gabay's thesis, the previous pictures and so on, and others that I'll show later. Maybe in my memory are attributable to a paper that appeared on the archive and was published by Jennifer Hahn. And so thanks to all of those who've contributed, may you recognize your own pictures and know that I'm very grateful for them. And we'll try to acknowledge them if anything is ever published, at least due to me. Now, let's see. So, okay, so we have David Gabay, 1986. That was really remarkable. And in fact, his thesis was the catalyst for me to try to understand how to create new knot invariants by studying the foliations and the C-star algebras associated to the foliations that came from Gabay's thesis. That led me to a time to go to Paris and later on to get involved with von Neumann algebras and the Jones polynomial. I never did complete this particular idea either. Another thing, another big event. So 1986, and then fast forward to 2020, when we learned that in fact the Conway knot is not smoothly sliced. Amazing result. And I imagine it has been discussed earlier in this meeting. And here is a picture of it showing of the Kinoshita-Terasaka knot, showing that it is smoothly sliced. I love these kinds of pictures because this is in fact a ribbon knot, and that's a picture on the right of a surface, which gives you the boundary of the ribbon showing that it's smoothly sliced. By the way, I think, in fact, if anybody is so motivated, I'm happy to take questions and perhaps maybe even respond to them if my memory is still operational. Okay, so for me, these are the highlights of my knowledge and learning about these two knots over the years since I was a graduate student at the University of Wisconsin. So follow up to this previous discussion about me trying to study C-star algebras and index theory to create a new knot invariant, that led me to a participation in a seminar in Paris, organized by Alain Cohn, and he had received a copy of a letter that Vaughan Jones had written to Joan Berman about his initial ideas. That was the catalyst for me and Raymond Licorice. The two of us appear in that little picture at the bottom from back in the day, to imagine that this Jones polynomial, this Jones-Skene relation that was implicit in the letter, led to all of these other polynomials. And so there is Vaughan Jones with the Humphrey group. Unfortunately, the two poles weren't there. They were, of course, on the other side of the Atlantic Ocean, but they should have been there, and maybe a little Photoshop would have done something. But anyway, there's the Jones, there's the Humphrey polynomial with the formula that Raymond Licorice and I, this was 40 years ago, I should remind people. Raymond and I just celebrated about 40 years ago with a quick visit to Cambridge. He's doing well. And so anyway, 40 years ago, we came across this polynomial business, and that led to a whole bunch of stuff, and much of which were catalysts for the talks in this wonderful conference, including, of course, Lou's discovery of his version of the Jones polynomial and the Kaufman polynomial. But anyway, so now we have these knot polynomials, and by golly, back in the day, we didn't really know what they were telling us other than being a tool to tell us if two potential knots were the same or not. In fact, I remember Michael Attia asked us once, how do you know these are polynomials? And maybe we have an answer since, I think so. But that was a measure of how little we understood back in about 1984, 85. So, okay, that led me to encounter biologists and apply knots to DNA, to DNA and enzymes. And then somewhat later, two proteins that Joanna talked about earlier today in one of the sessions. And so, stimulated by the challenge of finding a mathematically robust way to distinguish between the knots present in open chains and open arcs in space, in 2004, then Akash Dubey, Andrzej Stasiak, and I proposed a new strategy, which we thought was really quite crazy at the time, and it turned out it was something that I've been using ever since. The idea is simply to take your open arc, there's a picture of one on the left, a little random walk in 3 space, and then you have to close it up in order to apply knot polynomials. So what easier way than to sort of take parallel arcs from the endpoints and run them off in all of the possible directions off to infinity, if you wish. And that gives you a closed curve. You then calculate the knot type or the polynomial. And you do this for every point on a 2-sphere of directions. And so shown on the right here is a area faithful rendition of a 2-sphere. And the colors correspond to different knot polynomials. And so let's say the blue one, that's sort of like the ocean. That's a dominant one there, and that corresponds to a particular polynomial. And the red one and the green one and others would then to give you little areas on the two-sphere. And there are little areas there because this method is well defined, except for regions of area zero area. So almost everywhere this method works. It only doesn't work when you have crossings, self-intersections. Okay, so now you've got a rather nice, how to say it, collection of areas on the two-sphere, which are measurable, and so you calculate their measures and compare them. And so the blue is the dominant one. And so at the early days, we'd say, okay, well, that's the dominant knot type. Let's just call that open curve a knot of that particular type. Okay. The spectrum, however, is the then collection of knot types or knot polynomials. So when I talk about the spectrum, I'm thinking of a collection of two variable polynomials, in this case, Humphrey polynomials, and their relative or respective areas on the two-sphere. Okay, so that gives me a way of assessing the complexity of an open arc, either the dominant one, 50% or more, or maybe the whole spectrum, the whole range is sort of like in physics, a spectrum in physics with different frequencies, sort of how I would think of it, and gives us this collection of knot types. Okay, so there's a tool. And we use that then with Joanna and lots of colleagues to study knotting in proteins. But today I wanted to sort of think about knots coming from open arcs. All right, neat, okay. So here is a very simple case. In much of this, by the way, I'm plagiarizing myself. So this I found in a little paper, a draft of something that I had done. And so with this particular random walk here with some small number of edges, then I did the, computed the spectrum with 6,400 closures. I remember now my friend Eric Rodden said, but why would you do that? 100 is sufficient. And it probably so. But 6,400 closures gives you a much more robust kind of a number there. And here, in this particular case, then we see the unknot is 99% of the time, almost 100% of the time it's an unknot, but there are some hidden trefoils in there if you close things, if you're so fortunate as to close things properly. And so, the superposition, right. So what do I mean by the superposition of the spectrum? Well, remember my sphere with the colors. Imagine now that each color represents a Humphrey polynomial, a knot polynomial. So what one can do by virtue of a superposition is integrate those over the two-sphere, divide by the area of the two-sphere. So the superposition of a spectrum is simply the integration of the measure that is associated to that, evaluated on the polynomials. And so, okie doke, here is the answer for that. Let me see if I can actually go back. Oop, nope. For this particularly simple one, now the unknot, remember back as sort of an axiom, unknot is supposed to have polynomial 1, the scalar 1, okay? So, oop, wrong direction. So here, of course, the coefficient in my superposition is 0.9981, pretty darn close to 1. But the trefoil, the presence of these trefoils in some of the closures then enriches this spectrum to provide some indication of the extent to which you find a different knot type present in that particular configuration, okay? So the superposition then gives me a measure of how to assess the complexity of the configuration. Well, all right, good enough. A little coffee break. Now, I'm hanging around with lots of biologists, and so large, complicated two-variable polynomials as a measure of complexity of a configuration, a protein or a random knot or whatever, really isn't in their sort of spectrum, in their orbit of ideas of a useful measure. So my goal was then, okay, what the heck do I do to come up with a single number that expresses the nature, the character of complexity, that quantifies the complexity of this two-variable polynomial? Okay, so new idea. No, new idea. So I'm imagining I've got a two-variable polynomial with real number coefficients, like PLM there. And I imagine now that the exponents give me integer lattice points on a two-dimensional grid. So like the L is the X coordinate and the M is the Y coordinate. And so at the point ij in the XY plane, I have imagine a mass or a point with a real number associated to it, aij. Okay, so let's just take the absolute values of those numbers so that I can imagine those as being masses, all right, at that point, and thereby calculate the center of mass of this polynomial. Okay, interesting enough idea. Center of mass of this polynomial. So sort of tells you where this, how to say it, where this polynomial sort of is a cloud of points in the two plane, and sort of where is the center of mass of that. Now, I wanted to find a measure of the complexity. So the complexity then is given by the spread, the nature of the spread of these coefficients in the plane around the center of mass, and the way one would measure such a thing is with the radius of gyration. If the radius of gyration is 0, then you have all your mass at a single point. And if your radius of gyration is large, then this cloud of coefficients has important information spread out widely. Okay. And so going back to my previous polynomial, if I apply that to this polynomial, and if I've done it correctly with my little hand calculator here, then I find that the spread of this polynomial is 0.059297.4. In other words, it's not spread out very much at all. It's all very much concentrated around that point, basically 0.99 at the point 0, 0, right? Because those are the exponents of the scalar term in my two-variable polynomial. Okie doke. So now I have a way of expressing a single number, expressing the extent to which a two-variable polynomial, such as a knot polynomial, is spread out in the plane. And that could be a measure then of its complexity. Right. Okay. Now we're getting, I think, close to wanting to apply this concept, this notion to a particular example. Okay. And so I measured the Conway and the Kinoshita-Terasaka knots. Well, they can be, how to say it, created, can be represented by 11-edge equilateral polygonal models. This is due to Clay Schonkweiler and his student Eddie here from 2019, and they very kindly shared their coordinates with me. And then you can try to make the game a bit fairer by looking for the thickest version of these. So you wiggle these around a little bit so they are spread out as much as it can possibly be. In other words, you try to create a rope length maximizing version of these configurations. Rope length maximizing is manifested by trying to find the largest tubes embedded with these polygonal knots at their center. They're like regular neighborhoods of largest radius. So it's like a tube. And so, okay, you can do that. And here are these two configurations. And I suspect I put the Conway on the left and the Kinoshita-Terasaka knots on the right. Okay, so these are tried to be as similar as they possibly can. And that I also had a version of this with several hundreds of edges, which look as an approximation to smooth versions of the knots, but I don't share the data here today. So, okay, now we can apply our method. And so, okie doke, here we are. The Conway knot is the spectrum. The spectrum is, the Conway knot is in blue, and the Kinoshita-Terasaka knot is in red. And I should say, what have I done? Well, there are 11 edges. For each edge, take its complement. That gives me an open knot. And for that then open configuration, take its spectrum, compute its spectrum. That is, compute the array of knot polynomials coming from 6,400 different closures on the two-sphere. Do that for the Conway knot. Do that for each of its 11 edges. Okay. So that gives you now a whole pile of polynomials, and that gives you then a sort of spectrum. So take the union of all those, in other words, take the spectrum with the union, and do that also for the Kinoshita-Terasaka knot. Well, by golly, these two spectra look quite different. And you can see there, for example, they're similar. They have some similarities, but they're a little different. I'm going to see if I can point out, let's see, I should have oh yeah, there it is. So here, right here, I hope you can see this. There's a little blue edge right here. That blue one then is the Conway knot, but the Kinoshita-Terasaka knot actually is much larger here at this point. It goes up to almost 45% contribution. And I don't know what that means, frankly, but there is a way, that is a very distinctive way of saying these are different. What are these points here? These points on the y and the x-axis correspond to different knot polynomials. So this particular knot polynomial, and I unfortunately didn't look to see which one it was, then it's the Kinoshita-Terasaka knot is very heavily represented. That configuration gives rise to a very strong representation in that particular knot type. compared to the Conway knot. Again, I'm thinking about this as spectra in the sort of physical sense, as a signal that's going to identify the characteristic frequencies associated to an atom, let's say. Okay, and so here, down here is another place. There are other places where, of course, the Conway knot shines and gives you a much bigger contribution. Okay, so somehow this approach shows you that these two configurations of the two knots represent or have a very different quality of some character, of the character of which is mysterious. I can't tell you what the heck it's telling you, but it's telling you that there's something about them that is really quite different. Recall that the Conway polynomial that we had earlier, it looks about like this, right? Integer coefficients. It has in terms of the variable m, a scalar sort of portion, and then an m squared, and m to the fourth, and m to the sixth, okay? So already this is a pretty complicated polynomial, but when you look at the spectrum associated to each of those configurations, unfortunately, what you see is really quite different. Fortunately, what you see is really quite different. And there it is for the Conway knot. And of course, alrighty, the scalar, the m to the 0th power has contributions going from -8 to 10. All right, it's really spread out all over the place. If you look over there at the bottom, you see m to the 8th power. Remember, it's m to the 6th power was the highest one you see before. Those terms have very small values. And even the m to the 6th power doesn't have a huge value. It gets one that's like 0.2768 and so on, okay? So you get a spectrum, superposition of that spectrum, which is a rather complicated two-variable equation. And you do the same thing for the Kinoshita-Terasaka knot, and you get an equally complicated kind of polynomial. Now, recall that our challenge was to try to find a single real number that's going to express this, how to say it, the spread. I called it the spread. It's sort of like the radius of gyration of these polynomials. Okay, so we can calculate those. Oop, wrong way again. And so the spread of the Conway polynomial is 119, and the spread of the Kinoshita-Terasaka knot is 37. So, okay, somehow these are really, really quite different. In other words, the gap between those two values is about order of like 90. All right, that provided the sort of the measure that I was seeking to illustrate the fact that these two configurations are really quite different in some way or another. They're really quite different. Exactly what this means, because we're geometers, we're topologists. I mean, what's giving rise to this? That's the mystery. And that's the mystery that still remains from my efforts here. So to conclude, to sort of summarize, I've shown you a way to compare two comparable to open knot configurations, polygonal ones, because you can count the number of edges and try to make them as similar as possible, as reasonable, depending on your situation, and how you can try to measure the character closed configurations you can try to measure their difference there. The idea that I had and have is that this provides tools by which you can do this. And the mystery is, well, all right, you do this and you find out that they're really different, but what does this tell you about the geometry? What does this tell you about the topology? And that is, for me, an open question here. That's sort of like numerically useful, but conceptually, how do you, I'd like to have a sort of structural way of interpreting these to say these knots are really different. Okay. So anyway, thank you very much. There's Eleni from back in the day when we started talking about these, and myself, and I want to thank the organizers for this amazing opportunity to celebrate Luke Kaufman's 80th birthday.
Thank you, Ken. This was a fantastic talk. Really, thank you for doing this. There is a question. Let me first, I need to first stop recording because that's the arrangement.